All right, we're back, everybody. We're still in section 6.1, Introduction to Exponential and Log Functions. In this video, we're going to be talking exclusively about log functions. So, we ended last time with something like this, like what, excuse me. Let's get that pen. Y equals 2 to the x. And anytime mathematicians create a process of new mathematics is because they want to answer an interesting question. And the question that they wanted to answer is, how in the world do I get the inverse of this particular function? So we get the inverse by first, let's see, if we back this up, we can say f of x equals 2 to the x. And our first step would be y equals 2 to the x. And then our next step, when we talk about getting an inverse, would be switching x and y. So we could wind up with x equals 2 to the y. Now, mathematicians looked at this and said, how in the world are we going to solve for y? There's no conventional method by which we could get y equals, something just with x in it without having a y in it as well. So they said, we need to come up with something a little different. And what they came up with was a different kind of notation called logarithmic notation. Now let's review real quick. This 2 here, the 2 is the base of our exponential. Now this is called exponential notation. So exponential notation. And 2 is the base. Y is the exponent. And x, I'm going to call that, is the result. All right? And the reason I'm going through that is because when we change it to logarithmic notation, I wind up with y equals the log base 2 of x, where again, we call 2 in this case the base. So notice, whether it's in exponential or logarithmic notation, that 2 is still your base. Now notice here, we wanted to get something with y equals. Our logarithmic notation allowed that to happen. So y, was our exponent. And x was the result. So if we take the log base 2 of our result, we'll wind up getting back to what our exponent was in the first place. All right, now there's a couple of things in logarithmic notation. Our base, all right, we'll call our base, all right, will never be 1. Also, our base will always be greater than 0. And also our result, x, has to be greater than 0. And that certainly makes sense, because if we go back to our exponential notation, if our base is positive, right? If our base is positive, it doesn't matter what our exponent is, x will also have to be positive as well. So I need you to remember these two things, right? Because later on when we're talking about domain of logarithmic functions, it's something that we are going to have to deal with. All right, so basically what you can talk about here is that y is the power to which our base, in this case would be 2, is raised to get x. And this is something, once again, that I certainly want you to remember, because it's one of those things that is going to help you change things from exponential to logarithmic form, as well from logarithmic to exponential form. All right, so let's start by practicing changing exponential statements into logarithmic form. Why don't you guys pause the video, work through these three fairly straightforward examples, and we'll talk in just a minute. All right, so hopefully you guys were able to work through some of these examples. Let's talk about what you found. All right, so if you notice down here, I gave you both logarithmic and exponential form. And again, base goes with base, exponent goes with exponent, and then result goes with result. So let's take a stroke at some of these. So I always write log first, and I know my base is my subscript, so my base of my exponent's 1.2. So I'm going to put 1.2 down there. All right, and it equals, what does it equal again? It equals our result, right, of our result equals our exponent. So let me make that a little bit better. 1.2. So the log base 1.2 of m is 3. In the second one, I put the log base e of 9 equals b. Remember, our exponent is always what it equals. That was the question we were trying to solve when I started this particular lesson. And for the third one, I have the log of a, log base a of 24 equals 4. Now, in letter B, the log base e is a special log. E is a very special number. Some call it the natural number. Therefore, the log base e is the natural log. Back in the 1700s, when the French were at the forefront of mathematics, they called it log naturel. Log naturel, so we denote it as ln. So you could rewrite b as the ln of 9 equals b. I do want you to eventually get here. All right, so this is the final answer that I definitely want to see. And I probably would take off points if I didn't see you rewrite it in this form. All right, so if we can go from exponential to logarithmic form, we should be able to go from logarithmic form back to exponential. Why don't you guys pause the video, try out these fairly straightforward problems, and we'll go over them in just a minute. All right, so hopefully you got through all three of these problems without too much of an issue. Again, our base here is a, so that is the base of our exponential form. Over here, this is our exponent. Remember, we were trying to get our exponent by itself. So in exponential form, it goes back there, and it equals our result. So all I'm asking you to do in this particular set of exercises is to change from logarithmic to exponential form. There is nothing to solve here. Now again, in b, I have log base e. I could have written that as ln of b, and you shouldn't. I could have written it like this: ln of b equals -3. All right, so you should know that this converts to that, and then you get e to the -3 equals b. All right, and in the last one, we have 3 to the c equals 5. Hopefully, you were able to change from exponential to logarithmic form, as well change from logarithmic to exponential form. These forms are going to help you greatly in the next chapter, so you definitely want to get super familiar with them and make sure you can convert from one to the other fluently. Now, what are the advantages of logarithmic form? Well, in this next set of exercises, we talk about some of those advantages, basically saying that we could do things without a calculator. For example, if I have the log base 10 of 10, right, I can say since 10 to the first equals 10, the log base 10 of 10 is 1. All right, here I want to know what the log base 10 of 100 is. You might say, I have no idea. But if you think about it in exponential form, 10 to the second power equals 100. So the log base 10 of 100 would equal 2. All right, here I have the log base 10 of 1. And again, I'm going to look at it in exponential form. So 10 to what power would equal 1? Well, the only thing that fits in there is a 0, because anything to the 0 power is 1. All right, so this again would be 0. All right, so I want, now that I've given you the feel for it, I would love you to pause the video and take a shot at D through H. All right, hopefully by now you've worked through D through H. A couple of interesting questions in here. Let's explore these real quick. All right, so I have the log base 10 of 1/10. Now this is the first time we're seeing a decimal here. However, if we rewrite in exponential form, I have 10 to what power? Now instead of a blank, I could call that x equals, and remember, 0.1 is equal to 1/10. So I'm going to rewrite it as a fraction. It should help me out. Now, if I want to take that right side and rewrite it with the 10 in my numerator, I would write 10 to the x equals 10 to the negative 1. And in this case, what would x equal? X would equal negative 1. So that would be our answer. And for E, it's a very, very similar problem. I would write 10 to the x. And over here, this is 1/100th. So 1 over 100. And then that would be, excuse me, 10 to the x equals 10 to the negative 2. So x equals negative 2. All right, now F and G are kind of interesting, because if I take the log base 10 of 0, the question I have to answer is 10 to what power would equal 0? Now, if I put in 0, I would get 1, right? 10 to the 0 would be 1. And if I put in 10 to the negative 1, I would get 1/10. Remember D? 10th, right? So if I put in 10 to the negative 2, I would get 1/100th. So is there a number that I could put in my exponent that will yield me 0? The answer is no. So there is no solution to this problem. And remember, we talked earlier, our result, right, in this case was x. So our result has to be greater than 0. Otherwise, the logarithmic form just won't work. All right, and let's take a look at G. I have the log base 10 of some power equals negative 1. So that I'll write over here, 10 to the x equals negative 1. Now, if I have a positive base, there is no power I can raise it to get a negative result. So again, I will refer you to the conclusion we made up in F, which was that the result has to be greater than 0. And this factors into our domain. So this is something to keep track of. So in this case, H is our conclusion. It says that x must be greater than 0. right. So let's talk a little bit more about domain. All right. The domain of the logarithmic function equals the range of the exponential. This is a property of inverses. The range of the logarithmic function equals the domain of the exponential. So you don't necessarily need to memorize these, because if something is outside the domain, if you put it into an equation, it simply wouldn't work. All right, so let's go on to just a couple of problems. All right, so why don't you pause the video and take a look at some of these and try to determine what the domain of each logarithmic function would be. All right, hopefully you're able to make it through at least A and C without a problem. B is kind of an interesting one, so we'll take up that one last. All right, for A, I have my result x minus 2, and we said that that has to be greater than 0, and it can't equal 0, so it has to be greater. So I could say A, if I added 2 to both sides, has to be greater than 2. Or actually, I won't say A, I'll say X. There we go. Now for C, again, fairly straightforward. I have my x minus 1, but notice it is in absolute value, which means that it doesn't actually matter what x is, because if we're taking away 1, doesn't matter if it's negative or positive. The absolute value will always make it positive. So the only thing we have to worry about is the result being 0. So x minus 1 can't be 0. So if we add 1 to both sides, we can say x is not allowed to equal positive 1. Now, in both cases, I definitely would love to see interval notation. That is something that we talked about earlier in the semester. So if I have x is greater than 2, so I put a parenthesis 2 comma infinity. And for x can't equal 1, you put negative infinity all the way to 1 in union with 1 to infinity, using parentheses both times to talk about the infinity and the 1 both not being included. All right, so let's take up B. Again, B is an interesting one. So let's start our result. Remember, so our result is x plus 3 over x minus 1, and it cannot equal 0. All right, so let's start there. If it cannot equal 0, that means x plus 3 cannot equal 0, because remember, 0 over any number is just 0. So as long as the bottom's going to be a number, right, we could say x can equal 3. And that is the first thing that we are eliminating from our domain. All right, now if we look at our bottom part of our function, x minus 1, remember the bottom can never equal 0. So we can say x minus 1 can equal 0. So if we add 1 to both sides, actually this should be negative 3, excuse me, x can't equal positive 1. So here are two numbers that we have to eliminate from our domain. Now the question is, are there any other numbers we have to eliminate from our domain? If we have to eliminate them, it's because it makes everything in this parenthesis a negative number, or it makes it equal 0. Well, we've taken out the two numbers that would make things equal 0 or undefined. Are there any other numbers that would make the result negative? Well, one way we can figure that out is we can test a couple of numbers. Well, anything greater than 3 is going to yield a positive number, right? Let's say, for example, I put in a 4 here, and I put in a 4 here. 4 plus 3 is 7. 4 minus 1 is 3. We will always have positive numbers. If you put in 5, 6, 7 on up, that's what you will see. All right? So now let's take a look at less than negative 3. So for example, negative 4, if I say negative 4 plus 3 equals negative 1, negative 4 minus 1 is negative 5. So while I have a negative in my numerator and my denominator, when I simplify this, it simplifies to 1/5. Now the question is, no matter what number I put in, would I get that result as well? So let's take a look at another number. Let's take a look at like negative 10 plus 3 and negative 10 minus 1. So negative 10 plus 3 is negative 7. Negative 10 minus 1 is negative 11, which again would result in a positive number. So it looks to me like these are the only two numbers that would be eliminated. So the way we would write this in interval notation would be negative infinity up to negative 3 in union with negative 3 up to negative 1 not negative 1, but 1 in union with 1 to infinity. I'll make a little bit better U. There we go. And that would be our domain for B. Like I said, B is a kind of an interesting problem. So, and it's one of those things where testing some numbers sometimes will tell you a lot about the domain. All right, so we said that one of the advantages of logarithmic form was the ability to do a certain amount of these problems without a calculator. So why don't you take a look at A through F and see what you can do. We'll talk about a few of them in just a minute. All right, so hopefully you made it through at least a few of these without too much of a problem. A couple of these, A, B, D, and E, can all be done with a very similar method. So let's take a look at one of them. Hopefully that will yield fruit for all of them. So I'm going to take a look at B. And I'm just going to say 2 to the 16th equals x. Now, if you know your powers of 2, that's one thing. If you don't know your powers of 2 and you're unsure of the result, I can convert to exponential form, which would be 2 to the x equals 16. Now, in this case, 16 can be rewritten as multiplication of 2s. 2 times 2 is 4, times 2 is 8, times 2 is 16. So I could say 2 to the x equals 2 to the 4th power. And in that case, x would equal 4. You can use a very similar method with A, D, B, and E. Let's take a look at E. Let me get rid of this so I can take a look at E. Right, now again, I don't necessarily know my powers all that well, so I'm going to just rewrite in exponential form. 6 to the x power equals 1. So I say, how in the world can I start with a 6 and end up with a 1? Well, the easiest way to go is to say that x would equal 0, because anything to the 0 power would be a 1. All right, so let's take a look at C and F. C and F are kind of interesting. I'm going to use a similar method. However, we're going to see that we're going to get something slightly different than the others. So for C, I can say equals x. So that would be 1/3 to the x power equals 9 if I change it to exponential form. And this is problem C. Right? And if I have 1/3, I could say 3 to the negative 1 raised to the x power equals 3 to the 2nd power. When I raise a power to a power, I do multiply. So that would be 3 to the negative x equals 3 to the 2nd power. So in that case, negative x would equal 2, and x would equal negative 2. So for C, this was the first time that we got a negative result. Or a negative power, excuse me. In F, we're going to do the same thing. 4 to the x power equals 1/2. So that's 2 squared to the x power equals 2 to the negative 1. Excuse me, that should be an x. So then I have 2 to the 2x equals 2 to the negative 1. And we wind up with 2x equals negative 1 and x equals negative 1/2. So not only did I get a negative value for my exponent, I got a fraction as well. And that's just fine. So be on the lookout for those problems where you can convert to exponential form and you wind up getting a fairly nice result. All right, and we're going to use that idea to talk about graphing logarithmic functions. Now, when we graph logarithmic functions, I like the use of plotting points. So I'm going to create an XY table. Here I'm showing you my XY table. Actually, I'll take that away for just a second because I want to show you kind of what I'm looking at. So if I have y equals the log base 3 of x, right? And so I'm plugging in a number into here, and I'm getting my output over there. So if I were to change this to exponential form, I would have 3 to the y power equals x. All right, so this is going to be much, much easier to figure out what y is if I know that x is a power of 3. So I want to know that what's in my parentheses is a power of my base. So what numbers are powers of 3? For positive numbers, well, 3 to the 0 power equals 1. 3 to the first power equals 3. 3 to the second power equals 9. So 1, 3, and 9 are all potential values for x. All right? And then if I wanted to get a couple of negative values, I could say 3 to the negative 1 equals 1/3. 3 to the negative 2 equals 1/9. And 3 to the negative 3 equals 1/27. At that point, we're getting pretty small. But these also could be values of x. So I'm going to erase for just a second. So take a minute, pause the video if you want to write some of this down. Okay. So notice here, I said my first value I'm going to plug in for x was 1/27, then 1/9, then 1/3. And all I'm doing in my chart is I'm doing the legwork to get y. Remember we said that 3 to the y power equals x. So my exponent is my actual y value. So why don't you take a minute, work through a few of these on the chart, and just double check to make sure that I didn't make any errors anywhere. All right, hopefully you worked through some of the calculations and you wound up getting the same numbers that I got. Now at this point, notice here, I created all of my ordered pairs. So it would just be a matter of plotting these points on your graph to show what the graph of a logarithmic function would look like. So why don't you pause the video, take a minute, and plot these points on your graph. Okay, so you're looking at these points saying, how in the world am I supposed to know where 1/27 is, 1/9 is, and 1/3? Really, you're not supposed to, especially when you're hand drawing your graph. the best you can do is estimate. As long as you understand that 1/27th is a smaller number than 1/9 and should be closer to 0, and 1/9 is a smaller number than 1/3, you should have gotten a graph to look something like this. All right, so notice I put in my points. So after 9, 2, looks like our graph was getting fairly large. I think this is probably the easiest way to do the graph, is to say I need powers of my base to put in for x, and that will get me some nice round y's. The second method you can do, if you got really good at plotting exponential functions, is you could use the idea of the inverse function. Now, if you notice here, the idea of the inverse function is that my graph here and its inverse would be a reflection across the line y equals x. So if you got really good at knowing where the exponential function would be, and you were able to reflect across the line y equals x, that would be something that you could do. I find that students find this fairly difficult. So there's another one. There's 2 to the x and the log base 2 of x. And there is yet another one. Like I said, difficult to do. All right, so here are some properties side by side of exponential and logarithmic functions. Again, I don't necessarily endorse memorizing properties. I really enjoy looking at graphs and finding these properties. So most of these we've talked about already. I'm not necessarily going to go through them again. All right, so over here, once again, I want to go back to the idea of transformations. Just because we left the transformation section doesn't mean that we shouldn't exercise our skills. So why don't you pause the video? I want you to do this in 2 parts, and we're going to go over part 1, which is just for each letter. I want you to write down what the transformation is doing, and then you're going to make the graph, and we'll talk about it in just a minute. All right, so let's take a look. For A, we had this +2 over here. And what that +2 does is it actually moves our graph up 2 units. So if we look at our graph, remember log base 3 of x was down here. We graphed that already. And you could have used that graph if you had wanted to and just transform the points up 2 units. All right, so B, let's go back a slide and just take a look at B. B had a -1 inside our parentheses. And what does that wind up doing? That winds up moving our graph to the right 1. So again, log base 3 of x, you can again just transform the points over 1. Shift 1 to the right. All right, for C, the negative in front of our log reflects the graph over the x-axis. This one would be a little bit harder. But if you took the point and just said, whatever my x was, I would take the negative of it. So for example, my x or my y was at 3 was +1. So I would take that and say 3, -1. And again, it would go up this way. Lastly, if we put the negative on the inside, that translates it over the y-axis. So if we had +3 for our x, it would translate to -3 for our x, and the y would stay the same. All right, so again, transformations becomes a little bit difficult, but if you understand what the transformation is, it could make doing the graph just a little bit easier if you're given the parent graph. Now, we spoke earlier about natural log, and natural log is log base e. So if I had the exponential function y equals e to the x, and there is my line y equals x, right? The inverse is the mirror across that line. All right? And again, we call this natural log. All right, so here is your parent graph. Now for natural log, I probably would give you the parent graph because we are graphing by hand. But I definitely want you to know what transformations you're doing. So for example, the -2 will shift it 2 units to the right, and the negative in front of ln would do what? Would flip it over the x-axis. So I would start by flipping it over the x-axis and then moving it 2 units to the right. Why don't you pause the video for just a minute? Why don't you do your graph and answer the other questions? All right, so let's start. So what you'll notice I did here was I flipped everything over the x-axis. So let me get my laser pointer. I have e comma 1, and that translated down to e comma -1. And then I had 1 over e comma 1 translates to 1 over e comma -1. So that winds up making that change in shape. And then when we move it 2 to the right, notice everything moves 2 to the right, including my asymptote. My asymptote goes from x equals 0 to x equals 2. And my shape stays the same. But notice here, right, I have 1 over e plus 2. I have e and e plus 2. All right, so we're adding 2 to our x value. All right, so again, do the domain range. Our vertical asymptote was x equals 2. Let's go to the last problem. The last problem, once again, I really do want to talk about the graph. So I want to know what the 3 does, and I want to know what the -1 does. Why don't you pause the video and think about it and try to make a graph. All right, so this is the last problem of the day. Here is your parent graph. Now my parent graph is the log of x. So if I plugged in x equals 0, right, 10 to the what power is, if I plugged in 1, 10 to the 0 power is 1, so that's 1 comma 0. And if I said log base 10 of 10, I got an exponent of 1. So these are my 2 points for my parent graph. Now what's going to happen when I put my -1 in? It moves it 1 to the right. And notice it moves everything 1 to the right. So I move, my asymptote goes from x equals 0 to x equals 1. And then when I multiply by 3, it is indeed a vertical stretch. So notice 2, 0 doesn't do anything, because if I put 2 minus 1 is 1, the log base 10 of 1 is 0 times 3, still gives me 0. And then I get 11/3 because, right, multiplies by a factor of 3. So this would be my final answer right here. I hope you got an introduction to logarithmic functions. We'll follow up in the coming days with some more properties of logarithms.